Hi everybody, welcome to the second video for your Physics 1 course. Hopefully as I go along these things get better, more useful for you, maybe a less thick accent, we'll see. Alright, 4.31 is also a problem recommended by your course director. It's also a very general physics problem found in many different books. And it deals with a problem where some mass M is being held by some rope T, so some rope with a tension T, and this rope, like every other physical rope, has a maximum tension it can withstand before it breaks, and we call that Tmax. For this problem, we raise the mass by some height d during a time from t equals 0 to some time t. And what they want in this problem is to see how fast can I raise this without breaking the rope. So the faster I raise it, then the lower the time it takes to travel that distance d, and we'll call that minimum time Tmin. All right, when you try to do this problem, once again, you have to diagnose what type of problem you're dealing with. You're dealing with forces, so you may have to use sum of forces equals ma, and acceleration. Also, you're dealing with not only acceleration, but with distance and time, so you want to use the kinematic equations for constant acceleration. And we know that this acceleration is going to be constant because the tension should be constant and the gravity, the weight is also constant. All right. Once we understand those concepts and realize we have sum of forces equals ma, it's always good to write your body diagram. They didn't tell you that there was a friction on this body, so we're not going to have to worry about frictional forces. All right. Next concept is deciding whether my acceleration is going to be 0 or non-zero. So this thing is moving, then I know the acceleration will not be 0. I'm sorry, not because it's moving. I know it's accelerating because I started with a velocity of 0 and eventually started moving. All right, so to solve this, actually, before I go further, this is one of the type of problems where it's not obvious to see how you're going to get to the final answer at the end. These problems can be a little difficult and daunting because you have to set a bunch of equations up, and you're like, how in the world am I going to get to the minimum time from all of this? But what it helps is just keep solving the equation little by little, then eventually you'll see that it's solvable. So for example, we're starting with sum of forces equals ma. We can go ahead and write down that T minus mg equals ma. I'll leave it as a and as ay to keep it simple. Then I have t's, I have distances traveled, y2 minus y1 is the same as d, and I have acceleration. So the kinematic equation I want to use is y2 minus y1 is equal to v1t, the initial velocity, times the time, plus at squared over 2. Now, don't make the mistake of thinking this is equal to 9.8 meters per second squared, or the negative of it. That will be the case that will be the case if only the weight was acting on it. But the tension is going to give you a acceleration with less magnitude than 9.8. All right. The y2 minus y1 in this problem is equal to d. The v1, the initial velocity is 0, plus at squared over 2. So I get that the acceleration is proportional to 2d over t squared. All right, the next concept here deals with the maximum part of this problem. So if I want to have the maximum acceleration, I'm going to have the maximum tension. Now, similarly, over here for the kinematic equations, to get the maximum acceleration, I will have the minimum time to go all the way up there since they're inversely proportional. And now I start seeing how I could actually solve this. I can plug in the A max I get from this equation all the way up here to get the following. Then after that, it all becomes algebra. As pesky as it is, it's still algebra. I solve for t min squared and get the following. And that's your final answer. If you plug in the problem, if you plug in the numbers given by the book, then you will get 2.59 seconds. All right, so to review everything again, recapitulate. We first drew the whole thing. We realized that we have a sum of forces equals ma problem, but since I'm dealing with t and d, the time and the distance, I'm going to have to use kinematic equations. I set up a body diagram, and I recognize I did not have an acceleration equal to 0, and that will later, as we find out, will later be useful to find out the final answer. We set up the sum of forces equals ma problem, then combined it with the kinematic equations, did a bunch of algebra, and got the final answer at the end. All right, everyone, I hope that's useful, and see you later.